Good morning, everyone. First of all, thank you for the interest in joining our first webinar provided by the Graphia project, which is basically just going to be a basic introduction into knowledge graphs. So just to give you a little bit of context, so my name is Sai Holsinger. I'm the CTO at the Operis Research Infrastructure, which is a research infrastructure dedicated to open scholarly communication in social sciences and humanities. And I will be basically the project coordinator for Graphia as a whole. So Graphia is a 3-year project that kicked off in January, and we'll be building out a knowledge graph dedicated to social sciences and humanities, as well as having some modules, AI modules to help enhance the knowledge graph. But we also won't be working in a black box, but we have already included a number of different existing knowledge graphs that we will then integrate with, as well as a number of use cases that can basically prove out the knowledge graph solution itself, as well as enhance it and to ensure that it's being used in practice. So basically, when we're building out a knowledge graph, which is becoming a very popular approach, we thought it might be useful to basically, make the entire community basically aware of, well, what exactly is a knowledge graph. I think this is a perfect jumping off point for the project, and I'm grateful and happy for Julian Homo, who has put together the information, serving as the technical coordinator for the project as a whole. So don't want to take up any more time, and happy to pass over to Julian and we can jump into the content. So once again, thanks to everybody for your interest in joining this first webinar, and I hope you enjoy it. So Julian, floor is yours.
Thank you, Sai. Just before to start, could you confirm you can see my screen correctly
Yep,
right
looks
now?
good.
Okay, thanks. So we will start. Welcome to the first Graphia webinar, and thanks a lot for joining. My name is Julien Homo. I am data architect and the CEO of Foxcub, which is a French company specialized in large-scale graph technologies and knowledge infrastructures. I am the technical coordinator of Graphia, helping define the architecture and guide the development of our knowledge graph for the social sciences and humanities. During this session today, we will explore some key questions to better understand the landscape of knowledge graphs, with some quick questions like, for example, what is a knowledge graph really? Do they necessarily rely on graph databases? How are they being used today, especially in academic and research infrastructures? Who are the main players driving the knowledge graph ecosystem? Or, for example, what makes Graphia knowledge graph different? Of course, whether you are a developer, researcher, infrastructure manager, or just curious about knowledge graph, this session is designed to open up the conversation. We are here to clarify concept, surface insights, and share how Graphia is contributing to the evolution of meaningful interoperable knowledge system for SSH. So let me give you a quick overview of the summary for this webinar today. We will start with the basics. What is a knowledge graph? Then we will dive into how to build one, from data modeling to implementation. After that, we will introduce Graphia and its approach to the next generation of knowledge graph for SSH. And finally, we will wrap up with a Q&A session, so feel free to note down any question as we go or directly in the chat. So let's start with something simple. We are talking about knowledge graphs, but what do they actually look like in practice? First example, if you Google Ada Lovelace, you will see an info box pop up on the right-hand side of the screen. That is Google's knowledge panel, powered by what they call the knowledge graph, which is a centralized collection of facts, relationships, and entities presented in a user-friendly way. Then you have Wikidata, the free open structured knowledge base related to Wikipedia. Take the entry for Beethoven, for example. you will see dozens of properties: his birthplace, his composition, connection to other people, concept works. It's a fact graph. Anyone can edit. That is a knowledge graph too. In the scholarly world, there is OpenAlex. It maps author, institution, publication, and citation, all in a structured graph. It helps understand how science is connected, who works with whom, and how ideas are shared. This is definitively a knowledge graph too. In industry, to take another example, companies like Siemens use internal knowledge graphs to model products, processes, and systems, for example, in manufacturing on digital twins. It's a different scale, but the logic is the same, connecting data points meaningfully. And finally, there is the classic Neo4j movie graph, a sandbox where developers can explore how to store and query a graph of movies, actors, and directors. It is the most graph native example, built directly on graph technology and often used to teach graph concepts. That is also what some call a knowledge graph. And as you can see, we have one label, but many realities, and all of them are knowledge graphs. But here is the thing. Knowledge graph is not a technology or a standard. It's a broad, evolving concept, and its meaning often depends on who is unique and for what. For some, knowledge graph is RDF triples and ontologies. For others, it's property graph and AI-powered tools. And in many cases, it's just a pragmatic way to connect and expose complex data together. And yes, sometimes it's also a buzzword, a marketing shortcut to signal innovation, structure, or intelligence, even if the underlying implementation isn't really a graph. This flexibility is not accidental. As shown below, the knowledge concept sits at the intersection of AI, databases, and knowledge integration, three traditions that have shaped its evolution in different ways. A widely cited survey by Hogan et al. In 2021 offers a unifying definition. A knowledge graph is a graph of data intended to accumulate and convey knowledge about the real world, with nodes for entities and core concepts, and edges for the relationship between them. This is the baseline we will use moving forward. Of course, it's not meant to restrict what we explore, but to ground the rest of the session with a common reference point. But let's take a quick step back. We have been talking about knowledge graph. Okay, but do we really know what a simple graph is? At its core, a graph finally is just a shape. It's a structure with nodes and edges. That's all, more or less, of course. It connects things, sure, but it doesn't say what those things are. You have seen graph 1,000 times. The metro map in your city, that is a graph. A protein interaction network in biology, still a graph. Your LinkedIn contact network, absolutely a graph too. So here is the catch. None of those are knowledge graphs. Why? Because they lack meaning. A knowledge graph is a graph with semantics. It knows what the nodes represent, people, institutions, concepts, and what the edges mean, like, for example, authored by, located in, sites, works for. It is the difference between having structure and having a structure that actually tells you something about the world. Think of it this way. A metro map is a graph. A GPS with routes, place, types, and contextual info, that's a knowledge graph. A list of contacts, it's just a graph. A CRM that knows who is a client and what their journey looks like, that is a knowledge graph. A movie cast list, a graph. A a graph that knows, the roles, genres, and release dates, now we are in knowledge graph territory. So now that we have seen what makes a knowledge graph different, let's look at what that really brings. Because semantics don't just make things clearer. They are what allow us to go beyond navigation, to interpret, to align, or to reason. Without semantics, you can follow links, sure, but you don't really understand what they are. There is no way to explain what you find or to build trust in the data. But once you add semantics, once nodes represent things and edges mean something, suddenly the graph becomes usable in new ways. You can query by concept, not only by string. You can connect data across silos. You can build AI models that actually understand the shape of your domain. That is why semantics matter. They turn a graph into something explainable, reusable, and interoperable. And that is also where many misconceptions still exist. People often think of a knowledge graph as just a metadata graph, a slightly smarter relational database. But that is only the beginning. A graph of relationships is not yet another graph. The real shift happens one level deeper when the relationships are typed, constrained, and explained, when the graphs start to carry meaning. That is the difference between a graph you can navigate and a graph you can reason with. So the real power of knowledge graph is not in the shape, is in the semantics. That is what lets you build smarter queries, cross-domain alignment, and even new AI use cases. So let's go concrete. I have just mentioned that knowledge graphs aren't just a fancy way to organize data. Indeed, they solve real problems that researchers, institutions, and developers face every day. Let's start with a familiar pain point. We cannot connect our datasets. Imagine a public health researcher working on disease, treatments, on demographics. But their data lives in 3 different systems, each with its own schema. Knowledge graph can offer a common semantic layer that links them without needing to rewrite everything. Another example. We don't know if is this the same person or not. If G. Smith in HAL is also John Smith in Scopus. Maybe, or maybe not. A knowledge graph helps with this kind of identity reconciliation using contextual cues. It's about smarter matching across fragmented data. Then there is this classic issue. We are not finding what we are looking for. You are a PhD student searching for climate justice, and you miss 80% of the relevant article because they use different wording. A knowledge graph can surface related concepts and synonyms, making discovery more semantic, not just lexical. For the fourth example is one which is close to home in the age of LLM, or AI is accurate, but dumb. An LLM suggests a cancer research grant for an archaeology project. That's a mismatch. Knowledge graph are structure, sanity, and domain grounding. So models generate results that make sense in context. And finally, we don't understand what is going on. Anomalies in budget reports. Is it a fraud? Is it a mistake? Without traceability, you are stuck. A knowledge graph can expose the hidden relationships through the flow of data and help you reason about cause and effect. So, yes, knowledge graphs are not just a tech buzzword. They solve real day-to-day problems by connecting what we know, making it usable, and making it trustworthy. And knowledge graphs are no longer niche or experimental. there are no recognized market segments with a value of over $1.1 billion in 2024 and projection pushing that number to as high as $7 billion by 2030. Depending on the source, growth rates vary between 17% and 36% annually, which means that the market could triple in the next 5 years. Adoption is led mainly by North America, but Europe is following closely, and the Asia-Pacific region is seeing rapid uptake. Meanwhile, Gartner has positioned knowledge graphs on the slope of enlightenment in its 2024 hype cycle, a clear sign that we have passed the phase of hype and entered one of maturity and scaling. And where is this growth coming from? It's not driven by just one industry or one use case. Is it the result of multiple converging needs across sectors? We are seeing it in the rise of AI copilots and virtual assistants, which need structured, interoperable data to provide smart and contextual responses. We are seeing it in enterprise search and QA systems, where organizations are moving beyond keyword matching to actual knowledge-driven retrieval. We are seeing it in supply chain intelligence, where graph help uncover hidden dependencies and optimize decision-making. And we are seeing it too in digital asset discovery, powering new ways to navigate large fragmented datasets, whether in finance, academic publishing, or biomedical research. In short, this is not just growth, it is diversification. Knowledge graphs are becoming a connective tissue of modern data ecosystem. So yes, knowledge graphs are on the rise. We see growth, use cases, market traction. But let's not forget where this all began. Before knowledge graph became a business buzzword, before they were integrated into AI copilots or enterprise search tools, they were already quietly transforming academic knowledge. In fact, some of the most robust, durable, and open knowledge graphs were and still are being built in the academic world. So let's take a moment to look at the academic backbone of this movement, with 5 representative initiatives already operational, impactful, and often open source. We can begin with Open Citations. Open Citations is a fully open infrastructure that indexes millions of citations links between scientific publications. But it's not just a database. It's a response to the long-standing opacity of commercial citation indices like Web of Science or Scopus, for example. Here, everything is transparent, machine-readable, and aligned with FAIR principles. It uses semantic web standard to describe how one paper cites another, under what context, and even what kind of citation it is. Another major pillar is the open-air graph. This is one of the largest scale research knowledge graphs in Europe, developed as part of the open-air infrastructure and now part of the EOSC ecosystem. What does it do? It links project, dataset, publication, organization, funders, and data sources across Europe and beyond. It does not just collect metadata. It reconciles, aligns, and aggregates using mappings, ontologies, and open APIs. It's also impossible to discuss academic knowledge graph without mentioning Wikidata. You might know it as the backbone of Wikipedia structured content, but Wikidata plays a much broader role. It is a general-purpose collaborative knowledge base where anyone can contribute data about people, places, concepts, publication, and more. It serves as the central node in many scholarly workflows, thanks to different tools like, for example, Scholia, which can generate academic profiles, co-author graphs, and topic networks. Then we have, for example, the Open Research Knowledge Graph. Unlike traditional metadata repositories, ORKG focuses on the semantic content of scientific papers, not just who wrote what or when, but what the paper is actually about. It extracts and structures research contribution, hypotheses, methods, and comparison across papers, making it possible, for instance, to align different approaches to the same problem or map how experimental setups evolve. And finally, I would like to mention the computer science knowledge graph. This one is more domain specific. It covers over 24 million entities and more than 1 billion RDF triples extracted from scientific publication in computer science between 2010 and 2022. Its goal is to support meta-research, citation analysis, method tracing, and AI-powered scientific discovery. So knowledge graphs are already shaping the way research is organized, navigated, and understood. From generalist platform to domain-specific engines, they are becoming part of the backbone of modern science. All right, now let's open the hood. What is really inside a knowledge graph? Now we will try to answer to the following question: how to build a knowledge graph. You will hear in this section a lot about nodes and edges, and yes, that is part of the story. But it is more than that. First, in our knowledge graph, we have entities. These are the core things we care about: people, organizations, paper, datasets. Each entity has a type, like author, institution, um, publication, place, and properties like a name or a date. Then we have relationships. They are not just links. They are types and meaningful, as is affiliated with B. C cites D, this kind of relationship. This gives structure to the connection. Next comes the semantics layer. That is where we connect our graph to external vocabularies and standards. This is what lets your graph speak the same language as others, and what makes it part of a broader ecosystem. And finally, included in this semantic layer, you have the schema or ontology. It is what tells us what kinds of entities exist, what relations are valid, and how. So yes, it's a graph, but one with meaning, consistency, and rules. That is what turns a dataset into a knowledge graph. So now let's clear something up. When we say knowledge graph, many immediately think, so graph databases? It's a fair association, but also a limiting one. A graph database is just that, a database. It stores nodes and edges. It's great for exploring connection and running queries, but it doesn't make your data a knowledge graph. A knowledge graph is not just about storage. It's about meaning, again. It needs a schema. It needs semantics. It needs to know what a node represents, not just that it connects to another. And here is the twist. You can have a knowledge graph without a graph database. Some knowledge graphs live in relational databases. And the reverse is also true. You can have a graph database without a real knowledge graph. A bunch of nodes with edges labeled related to doesn't get you far. No semantics, no schema, no reasoning. So the real question is not what technology you use. It is how much meaning, structure, and interoperability you embed. That is where architectural choices come in. And that is exactly what we will look now. So if you want to build a real, usable, production-ready knowledge graph, you need more than data and, as we have seen, more than a database. You need foundation. And at the core, it comes down to three essential pillars. The first one is the interoperability framework. That is what ensures that your knowledge graph doesn't live in a vacuum. It allows your graph to speak the language of the wider ecosystem, whether it's using shared metadata vocabularies like DCAT, linking with schema.org types, or aligning with domain-specific standards like SKJEF. Without this layer, your graph is isolated. With it, it becomes part of something bigger, queryable, linkable, reusable. Second, the ontology layer. The ontology is your semantic backbone. It tells the graph what it's actually talking about, what counts as a person, a dataset, an institution, a contribution, and how all of this relate. It's where you define your domain logic. Whether you build it from scratch, aligning with existing ontologies, or mix both, this layer is key to unlocking semantic power and automated reasoning. And the third pillar is, of course, the architecture and the technology stack. This is your infrastructure, not just where the data is stored, but how it flows, scales, and connects. Is your knowledge graph centralized, federated? Does it rely on RDF stores, property graph, SQL backends, or hybrid? It's not about the one right way. It's about choosing a design that fits your purpose, your users, your governance. Of course, these pillars are just the core. Other elements, endpoints, API, interfaces, enrichment services, I don't know, all matter at the end, but they depend on this foundation being strong. And each of these pillars could be a full session in itself. So if you are curious about any of them, we would be happy to dive deeper after this. So feel free to ask more session about them. Yes, another topic. Um, sorry. Let's address one of the most common sources of confusion. When we talk about knowledge graph, many assume we are necessarily dealing with RDF and triples. Others immediately think of Neo4j and visual nodes and edges. So, at the end, who is right? Well, both, but they serve different purposes. RDF is the world of triples, a graph language that was built to be interpreted by machines and humans alike, with strong semantics, logic, and web standards. It is how you publish fair, interoperable metadata. It is why initiatives like Wikidata, OpenCitation, or ORKG use it. Labeled property graph like Neo4j is about analytics, AI exploration, and performances. You can store rich key value properties directly on nodes and relationships, which makes it ideal for graph computation, embeddings, or fast traversal queries. But here's the thing, they are not interchangeable. RDF is designed to mean something. LPG is designed to compute fast. So if you want reasoning, alignment, or public interoperability, RDF is your friend. If you are aiming for recommendation, analytics pattern, or machine learning exploration, LPG gets you there faster. And by the way, an RDF store without meaningful semantics can still be just a dumb graph. And an LPG can also be enriched semantically, even if that is not its native model. When it comes to adding the semantic layer, there is one question I often get. can we automate the construction of a knowledge graph? Let's take a moment to unpack that. In 2025, multiple strategies exist to actually semantize a graph. That is to enrich your structure with meaning, context, and alignment. And each approach has its own trade-off. Let's look quickly at 5 major family of techniques. First, there is the classic NLP pipelines. You extract entities and relations, so then try to link them to real-world identifier. That means to Wikidata, is out of to DB author, for example. It is reliable but often brittle and requires solid post-processing. Another technique is we now see a wave of LLM-based approaches that do everything in one go, triple illustration, typing, and mapping, all from a single prompt. That is powerful but fragile. You change the wording and you might get inconsistent or wrong result. Third, there are joint models trained directly on aligned RDF text corpora. This can predict entities, relations, and types at the meantime. They are accurate, but they need specialized fine-tuning and often don't generalize well outside their domain. Fourth, you can go from raw graph and bootstrap meaning with via similarity, embeddings, and rule-based logic. This is especially useful when no strong ontology is available or when your domain is too messy for supervised learning. And fifth, hybrid architectures combine both worlds. LLM extract content, ontology reasoner, check consistency. Shackle constraints validate strict. Shackle is another standard. It's more robust, and we see this powering next-gen architecture like Semantic Scholar OpenKG. So extracting triples is the easy part. Given them meaning, that is where the real world starts. And to close this chapter, let's spotlight who is shaping the world of knowledge graph in 2025. Well, it is not just one type of actor. It is a rich ecosystem where different players bring different strengths to the table. First, we have the semantic web veterans, names like Ontotext with GraphDB, Opening Software with Virtuoso, or another tool, AllegoGraph. These actors have been there since the early days of RDF, shaping the field around reasoning, linked data, and interoperability standards. Then come the LPG and native graph platform, Neo4j, TigerGraph, Cambridge Semantics. These are the ones pushing hard on performance, analytics, and large-scale graph traversal. They are behind many of the real-time exploratory and AI graph-based applications we see today. Of course, enterprise giants are in the game too. Amazon, Microsoft, Oracle, IBM. They integrate knowledge graph features into broader cloud infrastructures, often tied to AI services or data lakes. Their goal is scale, integration, and industrial robustness. And finally, we see a new generation of emerging and vertical players. Datavid, Clever, Pluri, Applied AI. They are exploring very specific domains, focusing on AI integration, performance gains, or novel ways to represent knowledge. So, what does all this mean? It means the knowledge graph ecosystem is anything but monolithic. It's fast-moving, diverse, and strategically balanced between 3 forces: semantic depth, graph power, and AI readiness. And if you want to understand where things are heading, you need to keep an eye on all 3. So now to conclude this presentation, let me briefly introduce the project behind our session today, which is GRAPHIA. GRAPHIA is a Horizon Europe project that brings together 21 partners across 11 countries, working over a period of 3 years from 2025 and 2027. The GRAPHIA central goal is to create a coherent and reusable knowledge infrastructure for SSH, ambitious in scope, yet grounded in real-world needs. This means tackling the long-standing fragmentation of SSH data, scattered across platforms, disciplines, and formats, and bringing it together into a single structured and navigable resource. Why does this matter? Because by doing so, Graphia aims to transform the way researchers visualize, connect, and analyze knowledge in SSH. It is not just about technology, it is about building a shared open infrastructure that supports research, discovery, and innovation at scale. Let's take a moment to zoom out and look at the big picture. What is Graphia really expected to deliver by the end of this project? First and foremost, it will provide the first large-scale knowledge graph specifically tailored for the social sciences and humanities, capable of integrating heterogeneous and currently disconnected datasets. That is a major milestone. Secondly, Graphia will develop a suite of open source large language model, the LLM for SSH series, designed to capture, generate, and reason over SSH-specific knowledge. Third, the project will deliver a set of new prototypes, putting the boundary in areas like thematic extraction, citation analysis, and risk discovery services, while also upgrading existing solutions. Fourth, at the heart of this development is a software framework for automatic extraction, enrichment, and publication of citation metadata, turning unstructured references into rich and machine-readable assets. Fifth, Graphia will expose its core services through a robust and modular set of API, enabling integration and reuse by third parties, including infrastructures, repositories, and tools. And finally, it will all be validated through a diverse set of 14 use cases, from academic pilots to applied research and industry collaborations, showcasing the versatility and practical impact of the platform. Each of these outcomes reflects Graphia's ambition to not only build infrastructure, but to reshape the way SSH knowledge is captured, connected, and used. Now let's have a look at the architecture we are currently building in this project. At the core, you will see 5 main building blocks. The data acquisition platform, which orchestrates how data is ingested, transformed, and integrated into the ecosystem. You have the green one, the data trust framework, which ensures data quality, provenance, and governance principles. At the middle, you have the SSH knowledge graph databases and technologies, or central technological layer where graph-based storage and querying takes place. We have also the graph-based services layer, which exposes advanced AI capabilities and next-gen SSH instrumentations. And finally, our integrity frameworks, which enables metadata harmonization across sources, foster alignment with community, EOSC standard, and of course, our APIs. But within this architecture, we are introducing a key innovation, the hybridation of RDF and LPG. This hybrid design allows us to combine the semantic rigor and interoperability of RDF with the flexibility and analytics power of LPG, particularly in contexts requiring interactive exploration and graph-based AI models. It is not just about using two graph models. It's about organizing their complementary roles. RDFs act as the authoritative, fair compliant layer that ensures consistency and reuse. And on the other hand, LPG supports exploratory analysis, embeddings, pattern detection, and AI-driven enrichment. This synergy is especially suited to the complexities of social sciences and humanities, where both semantic depth and dynamic navigation are essential. And to close this presentation, let's take a step back and look at the three core pillars currently guiding Graphia's approach. This slide brings together our current architectural choices, not as fixed decision, of course, but as a shared direction for discussion on co-creation across partners. And of course, the idea in this page is to link all the concepts I mentioned during this introduction with our current work in Graphia, especially around through these three core pillars. First, about the interoperability framework. We are aligning our work with the Scientific Knowledge Graph Interoperability Framework, which is SKGIF, the standard I have already mentioned during this presentation. This is to ensure that metadata is harmonized across communities. That includes mapping or model with some vocabularies like the Go triple vocabulary, some standard from EOSC, for example, and established ontology. Multilingualism and decentralized governance are key principles here, paving the way for federation and cross-knowledge graph querying at European scale. About the ontology layer, our goal is to ground the knowledge graph in actual SSR research practices. We are not reinventing everything. We plan to reuse and extend existing vocabularies like schema.org, triple, scores, and so on. The Graphia ontology will be designed as modular and layered, supporting both formal OWL structures and lighter typology like tags and classification. Everything is under discussion. This makes it suitable for gradual enrichment and cross-domain reuse. And finally, the architecture and technology stack. Here, we are moving toward a hybrid architecture, a triple store, a master one. This is our reference in the entire project. The triple store, like GraphDB, Virtuoso, or Clever, the discussion is ongoing about these three tools. So a triple store at the core, this is the fair compliant backbone. And Neo4j, the AI module key component, an analytical and AI-driven layer to perform graph analysis, embeddings, and LLM-powered enrichment. This hybrid approach allows us to separate semantic consistency from analytical performance and to scale flexibly. So again, nothing is final, but these three layers are emerging as the conceptual backbone of Graphia knowledge graph strategy. That brings us to the end of this journey through the world of knowledge graph and the Graphia project. I hope it sparked ideas, raised questions, and perhaps even some healthy doubts. Now, I would be to hear your thoughts, questions, or challenges for the last part of this webinar about Q&A. So thanks a lot for your listening.
Thank you, Julien, for this rich yet really easy to follow presentation on the knowledge graphs. I think I will stop the recording now to make you comfortable enough to raise your questions.